Hi, everyone. Thank you for coming. Today we have our speaker is Jeff Berman, who will speak with us about natural hazards reconnaissance. He is a professor in the Civil and Environmental Engineering Department at the University of Washington, and he usually conducts research in structural engineering with a focus on earthquake and natural hazards impacts on building and bridges. So take it away whenever you're ready.
Okay, thanks, Julia. So it's really, thank you for having me and letting me talk to such an excellent group of young students. And my hope here is to um, get everyone thinking about civil engineering a little bit and about structural engineering a little bit, and to see some of the really cool and interesting things that we're doing. I just wanted to make a little pitch because I think this is a group that could contribute in kind of helping to solve some of the great challenges that face us as a society, kind of as really human beings in the world. And so I listed some of what I think are some of the most pressing societal problems, the impacts of natural hazards and pollution and availability of clean water and adapting to climate change, urbanization, and the rapid development of countries who were lagging behind previously. And so all these create enormous problems. They are really, really challenging problems that really civil engineers are at the heart of solving. And one of the things that we're learning to do in civil engineering is to take all of these great modern technologies that we have and learn how to apply them to really advance, to really help solve these major problems. So for those of you who don't know much about civil engineering, I just wanted to make a little pitch about the discipline that I love and helping people and figuring out cool ways to solve these really challenging problems. Civil engineering is really engineering for society, making society better. And there's structural engineering, which is part of civil engineering, which is what I do. There's geotechnical engineering, which is thinking about tunnels and foundations and landslides and bunch of things like that. There's environmental engineering, making sure we have clean water and clean air. Mm-hmm. Transportation engineering, which I understand you've heard a bit about. Water resources engineering, which is making sure that we manage our water well and that we have availability of water. And then construction engineering, which is making all of these designs that come from the other parts of civil engineering actually happen. And figuring out how to build these big, fantastic solutions to these major problems. So I'm a structural engineer. I thought I'd just take 1 minute and talk about what structural engineers do. We ensure like safety and serviceability of structures, including bridges, buildings, other large components of infrastructure. We try to creatively and efficiently use materials to achieve our economic and sustainability goals. And we often work in pretty big teams that are involve people from a range of disciplines. And they could include architects and mechanical engineers and people who are helping us to actually make our designs a reality. And sometimes we get to do things that are quite beautiful and striking, like design this gorgeous bridge in Switzerland, just as an example.
Wow.
You can, Julie, please stop me, anytime we're going along, if there's questions and stuff.
Okay. Sounds
absolutely. Good. So another thing I wanted to point out that structural engineers do is, we design the kind of skeleton for these big, buildings and bridges and things like this. And It's a little bit different from designing other structures, right? So there are mechanical engineers who design, they might design bikes and cars, and they might even design like, this is maybe a little bit of an old slide. It should be iPhone, but they might design the case for your iPhone and stuff to make sure that your iPhone is robust. But there's a few things that set civil structures kind of a little bit apart from some of those other structures. And some of the things that we have to think about as civil structural engineers is really the scale of our projects are often very, very enormous. There's no prototyping, and we don't get to test our designs. We do a design and it's built and it's tested in the real world. And that's where we, there's no prototyping and chances to try things and get it right. Often our designs are not repeated. They're very unique. Here you see the Porta de Europa in Madrid, which is these two amazing buildings that are leaning, really, really interesting. There's only one of those in the world. Well, okay, there's two of them, but there's only, one set of those in the world. Then I think the consequences of failure for civil structures are really, really high, right? If a building fails or a bridge fails, there are really, really significant consequences to that. And then our designs have to operate in this really uncontrolled environment where we could have earthquakes and hurricanes, and they just have to operate out there in the environment. And that's why we have a whole licensure process. As a structural engineer, you have to get a license to actually design buildings and bridges. And they have huge social and economic impact, obviously.
I'm wondering, how long does it take to go through the entire process of making a civil structure, or including the planning? Well, I guess the planning and actually building it. How long would that take?
Yeah, so a building like the ones we're looking at, it might be a 10-year time frame from concept, from the point where whoever might own that spot decides they want to create this big building, through conceptual design and then construction, and by the time it's kind of open and ready to go, it could be as long as a 10-year process for these really major structures.
Wow. All right. Thanks.
Yeah. So I did say it's difficult. We can't test this full building, right? It's not really possible to test this full building here. This is, a steel framed building, and I don't know exactly what it's going to be, maybe an office building or something like that. But we do and can test, say, the material for the building, and we do that. So here's kind of just an example of in my lab, we're testing steel. Just to make sure we understand the material properties for this steel. We put it in a machine like this, and we push it and we pull it, and we're able to understand its behavior. In this case, in terms of what we call stress and strain, or you can think of it in terms of the force it takes to push and pull the steel versus the deformation of the steel, and that helps us understand its behavior. And we maybe can't test the whole building, but in my lab, we actually could test one of these big braces, one of these diagonal elements that actually makes up this building. And so here's an example of us testing one of these braces. And in this case, those braces they're there to resist earthquake loads and wind loads. And in an earthquake, we're going to expect them to go through really large deformations just like this in a really big earthquake. And the brace's job is to be damaged so that the rest of the building is not damaged. The idea is kind of like a fuse, in an electrical system, where the braces are the ones who are going to be damaged, much like the fuse is damaged in an electrical system, but everything else is okay. And that's how we're able to understand the behavior of a brace like this.
I wonder if this is like, sorry, another question. Well, like,
Yeah, no, it's great.
is this what they use in, because I know in Japan they have a lot of earthquakes, and I know they've built their buildings to kind of withstand those earthquakes. Do they use like braces like these in order to do that? Wow.
Absolutely. Yeah. And there's lots of different types of braces and things like that. And this is just one example. But yeah, absolutely. The technology used for resisting earthquakes in Japan and in the US, it's actually very similar.
Wow. Okay.
Yep. And and again, in my lab, we can't test the full building, but we can test, say, the connection. And so just an example of some of the types of tests that we do to understand the behavior of the connection. This one's slowed way down, and we're gonna see the failure of that connection, obviously. And my dog really liked it in the background there. Hopefully you didn't.
I heard a little bit, but I wasn't sure what it was. So
yeah, it's good. And then there are some big labs around the world, and while they're not big enough to test this entire full 3D building, they might be big enough to test this entire braced frame, so we can figure out how that behaves. And this is just a animation of some testing where we actually were able to test a piece of the building. It's not the full building, it's just one braced frame pulled out of the building, and we're able to test that all the way to failure. And you can see the braces fracture and do what they're supposed to do. And the idea with this is that the braces end up damaged, but the beams and the columns and everything that is kind of carrying the vertical load and where the people are is fine. And the building is safe after an earthquake. And you do have to go in and repair braces and things like that. And so what we do a lot of in structural engineering, and a lot of the work I do, is doing these kinds of tests both in the lab, and as we'll see, trying to learn a little bit about how things behave in the field too. But we try to then, once we understand the behavior in the lab, we try to develop these computational models that incorporate physics and a really good understanding of what's called mechanics, which is looking kind of at the material behavior and looking and trying to incorporate that into a complete model of the system. And so here's an illustration of us just testing a brace in our laboratory, and then us doing modeling in the computer that incorporates all the physical behavior that we observe in the lab. And then we're able to simulate that behavior in the computer. And that's great. That's how we're then able to go and design safe structures for things like earthquake loads. And we take these very sophisticated models and then we simplify them for the designers that might design this braced frame in design offices, like structural engineering design offices. And then they extend all of that and are able to design really large and complex buildings with the help of computers and with the help of models. And here's just one example of the 56-story LA Live building. This is the computer model that was used to help do that design. And so all this stuff is connected. We take our laboratory tests, we figure out how to do really good computational models, we simplify those models for design engineers to be able to use in practice, and then they're able to safely design the buildings and bridges that make up our infrastructure. So it's a whole process. But if we think about kind of what happens, what causes structures to be unsafe sometimes, what causes damage, there are natural hazards, earthquakes, hurricanes, tropical cyclones, tornadoes. There's man-made hazards, which could involve construction accidents, could involve overloads, or malicious acts even. There could be design errors or construction errors and oversight, lack of oversight. And much of the research and the new innovation that's happening in structural engineering is really aimed at improving structural safety in the face of these things that could cause structures to be unsafe. And one of our big questions is, how do we know that we're doing it right? And of course, I showed you some laboratory tests where we're working in our labs to test components and things, but we also have the observations from the real world laboratory. And that's what I'm going to talk about, is how we learn using all these new technologies, how we learn from the occurrence of natural hazards, and some of the work that we're really trying to do to help us understand how buildings and infrastructure perform in the face of large natural disasters. So I have a couple pictures here just from some natural hazards that have had impacts in different places. Here's a picture of kind of the heavily impacted area in Kobe, Japan, when that earthquake in 1995 struck, and it was a huge earthquake, resulted in hundreds of billions of dollars of damage and 6,000 deaths. It was a very, very extreme event. And then another one that I'll actually focus on, and I've done a lot of work related to Hurricane Michael. So Hurricane Michael happened in 2018. It struck the panhandle of Florida. You can kind of see the outline of Florida underneath here. That is actually the satellite imagery of Hurricane Michael as it is making landfall. And there weren't a lot of deaths in Hurricane Michael, thankfully, but it caused an enormous amount of damage. Thankfully, with hurricanes, we have a much more warning than we have with earthquakes. And of course, there was a huge evacuation effort for Hurricane Michael, and that's why the deaths were low. Uh-huh. So I help to run a center called the Rapid Facility. And what we do is we try to use all these modern tools and technologies, and we go after these natural disasters to try to figure out, to try to document how infrastructure performed so that we can learn from it. And that's what I'm gonna talk about. And I'll kind of rewind a little bit, and just to say that we've been learning from natural disasters for a really long time. In structural engineering in particular, structural and kind of geotechnical and really civil engineering all around. So here's a picture from the 1906 San Francisco earthquake. And here is a report that is an investigation of the impacts of the 1906 San Francisco earthquake. And it's really one of the first formal written reports learning from, in this case, an earthquake. And there were some really, really, really important ideas that resulted from this very early reconnaissance work. And what they did is they mapped the damage all across the city of San Francisco, which is much smaller then than it is today. They started thinking about things like, why is the damage more concentrated in certain areas? They learned things that are called site effects, which is really important in earthquake engineering. It's thinking about the local soil conditions. The soil conditions directly under buildings really impact the ground shaking that the buildings feel. And those observations really came from this early, what we call reconnaissance, natural hazards reconnaissance. And even as little as 10 years ago. So 10 years ago, there was this major earthquake and tsunami in Tohoku, Japan, and you may have read a lot about the major earthquake and tsunami in Tohoku, Japan. And a lot of folks from the US and from Japan and kind of all over the world, they went to Japan to try to figure out how we could learn from the impacts of that event. And at that time, you can see people making measurements here, right? And so this is a researcher, and they're trying to figure out how this building moved. And this building was subjected to what's called liquefaction. And that's when the soil underneath the building kind of moves around a little bit and gets really soft, and then the building sinks and tilts a little bit. And they're making measurements about how far this building sank and moved, but they're doing it by hand and, kind of charting it out and writing things down. And there's a lot of error in these manual measurements and stuff. But we were able then to understand what happened to these buildings and to think about how we could do things better in the future. But the center that I help run, this rapid facility, we're trying to use new, awesome, modern technologies that allow us to capture data at really high accuracy and get these real extraordinary pictures of damage to the built environment. So contrast those hand measurements that we were doing in 2011 with an investigation that we did in 2018 here. And here, this is using what's called LIDAR. And that's a laser system that I'm gonna talk about. And with LIDAR, we're able to send. So it's a laser beam, and we're sending millions sending the laser out millions of times and reading its response. And we set it up at a few different locations, and it's just on a tripod. And we can go to different locations, and then we can assemble all of this laser information into a 3D, it's called a point cloud. It's essentially a 3D representation of everything the laser saw. And there's a lot of work to kind of assemble this, but we're able in this case to get this full scene. So now, instead of just capturing the displacement of one of these buildings at one edge, we're able to actually capture the full 3D deformation of all of these buildings in this neighborhood. And you can see, we're kind of, you can see this building right here actually moved quite a bit. It sank quite a bit. And we're able to kind of, get this full 3D picture. And so it's really pretty amazing to be able to do this now.
Yeah. So is it like normal for the building to sink in earthquakes?
Yeah,
this is you're measuring it.
Yeah, it's called soil liquefaction and ground settlement, and it happens quite often in earthquakes. And it depends a lot on the local soil conditions and stuff. And we're still learning about soil liquefaction, and it's really important to be able to understand in design for soil liquefaction and be able to test the soils that we're building on, whether or not they might be subjected or they might be susceptible to liquefaction. In order to learn about that, we need all these case studies. Like, we need to know that this building settled, and then we need to go and figure out what the soil conditions were for this building, and then be able to know how much it settled. And so the development and capturing all of these case studies is really, really important for us to be able to figure out this type of damage that happens in earthquakes.
Yeah. Right.
So we have all these kind of cool tools that we go and we do natural hazards reconnaissance with. And I'll just kind of illustrate a few of our really neat tools. So we have a fleet of drones that we go out and capture images, as well as LiDAR. We have one drone that we actually can put a laser scanner on to capture kind of the same point cloud type information. We have a lot of image-based data collection that we do, and we've got some really cool systems for image collection that I'll show. We've got laser scanners, and we even have a drone boat that's able to map underneath the water, so it can tell us a lot about how, say, in a hurricane, you get these big storm surges, and they really alter the coastline and really alter what's underneath the water and in kind of the near shore environment. And it's important for us to be able to map that out too. And so we've got this drone boat that helps us do that as well.
Right.
So a lot of really interesting technology. And I'll talk a little bit about some of the pieces, some of the individual tools, and then I'll show one thing, really cool example, kind of in detail of what we've done to understand some building damage in Hurricane Michael, actually.
Right.
So we have all these amazing tools. We use advanced what we'll call Geomatics Technologies, and these are really being able to capture these 3D geometries of the built environment. And that's going to include our LiDAR equipment and things like this. We have a bunch of equipment that lets us instrument buildings so we can understand how they shake in earthquakes, and instrument the ground around buildings to see how the ground is moving in earthquakes. And often, earthquakes are unpredictable, so it's not like we can go and put these instruments out ahead of time, but there's often aftershocks after earthquakes, and that's where we go and we instrument a building. So once an earthquake happens, we get our instrumentation out really quick so that we can observe what's happening in aftershocks, and that still tells us a lot about how buildings behave in earthquakes. So we have a full list. We have all this different equipment, and I'm going to talk quite a bit about laser scanners because that's one of the ways that we can develop, capture these 3D images, 3D models of what a building looks like after a natural hazard. And I'll talk about then how we use that information to understand what happened to the building during the natural hazard. So we have a bunch of different laser scanners, and we don't need to know all those details. We also have a bunch of different drones, and the drones allow us kind of to do a little bit of what the laser scanners let us do, but on an even bigger scale. So here's a whole neighborhood that we were able to collect data on after Hurricane Michael. And this neighborhood is really, really big, and it would take us a really long time to collect information on this with our laser scanners. But instead, we're able to fly drones, and we use some really cool software that allows us to do what's called photogrammetry, or structure from motion. And we're able to take all of these images that the drones collect and actually put them together into a 3D model as well. So this is actually a 3D model of this entire neighborhood that was damaged in Hurricane Michael. And so we have lots of cool drones to do that. And like I said, we have one drone that's really special and really big, really complicated and hard to fly, but it actually has a laser scanner on it. So this is a little laser scanner down here, and that drone has lots of special features on it, so we know we can identify the exact, very precise location of the drone as it is doing its laser scanning down below. And here's an example of some of the data that we can get from this drone. So this is a really slow-moving landslide that's happening in Oregon along Highway 101 in Oregon. And they've had to rebuild. You can see the road here, and they've had to rebuild this road 4 or 5 times already because this slow moving landslide is happening. And so we go down to this landslide probably every 4 months, and we fly the drone with the laser scanner, and we're able to figure out how the landslide is actually moving and help Oregon State DOT figure out how to reinforce the hillside to slow the landslide down even further so they don't have to repair the road as much. So really kind of interesting and cool application of both kind of drone technology, but also laser scanning technology.
So this is still happening. Like you guys are still in the middle.
This is still happening. Absolutely. Right. Yeah. And we can't stop it. We can slow. You're kind of fighting against. Why is it happening? It's happening because this is a area that gets a lot of rainfall, and the slope, is just the composition of the earth, of the ground. It gets really saturated. It holds the water quite a bit, and then it just moves slowly over time. And so we can do things like provide better drainage. And being able to map out how the landslide is moving actually helps us design better drainage. It also helps us do things like, put some reinforcing in different locations within the landslide and put these big long tiebacks in. So they'll actually drill. Essentially, they're like big long nails, like 30-foot long nails that they're going to put in to the ground to help anchor the ground a little bit and help slow the movements down. But knowing how it's moving is really, really important.
How fast do they usually move? Like
this one is, landslides can move really, really fast, or they can move really, really slow. It really depends on
where it is,
where it is and what the soils are, and a lot of things like that. I don't know if you remember, but you could look it up. There was a landslide in Washington State called the Oso landslide that happened about, I want to say it was 8 years ago or so. And that one went really, really fast and destroyed houses, and there was loss of life associated with that. And so that's one example, and it was rain induced. And it was this example of kind of the ground getting so saturated, and all of a sudden a whole hillside just went all at once. So they can move really fast like that, or they can move much slower, like this one is here in Oregon. So this one's moving at a rate of, I want to say it's like 0.5 meter a year, something like that.
Oh wow! Okay.
Yeah.
So would that be considered pretty fast though, right? Or no?
Yeah. I mean, 0.5 meter a year is a big deal to this road, right?
Yeah.
If the road is moving 0.5 meter, this one section of the road is moving 0.5 meter. That means you have to repair the road every year, right?
Yeah. Exactly.
Yeah.
Okay.
Because it's cracking and it's not can't do that. And then so we've got all kinds of we've got really fun imaging equipment. We've got a couple different systems that are street view systems, and they're a lot like the street view systems that Google drives around. And in Google Maps, you can pull up street views that are these 360-degree immersive environments. And we've got 2 street view systems that are super mobile. They're a lot simpler than Google's Street View system, but we can put them on a car and drive around right after a natural hazard event to document that natural hazard event really, really well. And we've got all kinds of different imaging equipment in addition to the Street View that lets us put together really interesting. So this is a 3D model again, but this 3D model of this landslide was put together with images instead of laser scans. So it's not a laser going out; it's a series of images that because we can kind of know the position of the camera, we can understand. We know the position of the camera, and we know things about the camera, like the focal length and things like that. And that tells us if we kind of take pictures from different positions, we can figure out for each pixel in the image how far away that the image captured by that pixel was from the camera. And then using that information, we can assemble the images into a 3D model as well. And that's called photogrammetry, or structure from motion. And it's really a series of computer algorithms that helps us do this. And so it's very similar to where you've got in laser scanning, you have a laser that goes out and bounces back from a point. With photogrammetry, we're using an understanding of the pixels in the images instead.
So why would you
to put together
use
these models.
one instead of the other? Why would you use one instead of the other?
Yeah, that's a great question. And it really depends on how accurate you need your measurements to be. Photogrammetry is not as accurate as laser scanners are. So as a structural engineer, if I'm trying to measure deformations in a building, movement, how a building has been damaged, I probably want laser scanners instead of using structure from motion or photogrammetry, because I'm going to get much more precise measurements. But for things like landslides, sometimes, especially really big ones that are on really big scales, we maybe need accuracy that's on the order of centimeters, maybe 2 to 4 centimeter accuracy. And for that, structure from motion or photogrammetry is great. And that's the kind of accuracy we're getting. But with some of our laser scanners, we can get accuracy for each point in the millimeters, like maybe a couple millimeter accuracy. And so really, really precise imaging with the laser scanners versus the photogrammetry methods.
Okay, thanks.
And then I talked about our boat. We have a boat that we can send out and actually map the bottom of the surface as well. So that's kind of all of our equipment. And I want to take the last 10 minutes and show you one example of how it was used, how it's been used. And I'll take our Hurricane Michael work just to show you a little bit about that. So Hurricane Michael was a huge hurricane. It was a Category 5 hurricane when it made landfall. Its impact was really around Panama City, Florida, and Mexico Beach, Florida. Those were really the two communities that were heavily impacted. And Mexico Beach, which is a small kind of beach community, was pretty much totally destroyed by the hurricane. Almost every single building in Mexico Beach was destroyed. Panama City, which is a big city, had less damage, but it had some really significant impacts. And so like we said, there were maybe 16 direct deaths, but over $20 billion, near $25 billion in losses from infrastructure. And so here's just some images of some of the damage to the built environment from this hurricane, and it was really extreme. You can see some collapsed buildings. You can see this is a gymnasium at a school that's collapsed. You Here's an apartment building, residential apartment building. Here's a house that was picked up and moved by both the storm surge and the wind off its foundation, and moved quite a bit. And even bigger buildings with, that were made out of masonry and steel, bricks and steel and things like that, they collapsed as well. There was a lot of damage to roadways. There was a really significant storm surge associated with this hurricane, where the water level, it was near high tide when the hurricane occurred, and the hurricane pushed a bunch of water up on land. And there was it's called storm surge when that happens, and there was a major flooding event. And when the water comes in a hurricane, it's actually moving pretty fast too, and it can cause damage just from the flow of the water. So we wanted to look at, there was a really special project, kind of one focus that we wanted to have. And there was one observation that was made from the first people that went down and looked at the damage from Hurricane Michael, was that there was a lot of collapses of what are called large volume, low rise buildings. These are kind of warehouse type buildings, but if you think about what we use warehouses for, they're really actually important. There's lots of economic impact. When warehouses collapse, often they might be storing some of the critical things that are needed to recover from a natural hazard event. So we went down and we looked at what was the damage to these low-rise, large-volume buildings, and could we learn why they performed so poorly? And they really did. There was almost a 75% failure rate for large volume for these low-rise buildings. And so we went in and tried to figure out, what happened to them. So we went and we did very detailed studies of 9 of them. And we took our laser scanners and we went into these 9 buildings. And here's just a map of some of the buildings, a few of the buildings, and then a bunch of them were on this Air Force base as well. That it's called Tyndall Air Force Base, and it was heavily impacted. But here's a few of where the buildings were on a map, where the contours here show the wind speeds. And these wind speeds were huge, right? Category 5 hurricane has wind speeds over 170 miles an hour in some of these locations. So really, really, really fast, really strong wind. And here's a link, but hopefully this comes up. But there's a link there. If it will come up. I know it will. Okay, there it is. So I want to show you the point cloud that we collected from some of these damaged buildings and some of the really interesting things that we can do with the laser scanned data. So here's one of the damaged buildings, and this one was a marine storage building. Essentially, it was storing boats. And you could see in the front, it collapsed from wind on the front side, and I'll explain how we've learned how these buildings collapsed, and they all collapsed essentially the same way. And our work in reconnaissance has taught us how they collapsed, why they collapsed, and what we can do about it in the future. But here's the inside of this building, right? We're able to save this damaged scene in 3 dimensions, and we're able to come back now, 3 years later in Seattle and actually make measurements and learn from this collapsed building, even though this building's been torn down for 4 years since the hurricane. So that was one of them, and I have one more point cloud to show that is another building, and this one was a distribution center. It had all kinds of things in it. FedEx was using it as well. But this building, you can see the roof collapsed and one side of the building collapsed, and we'll kind of, do a little fly through of the 3D model of this building as well. And you can see we're able to throw away and clean out a lot of the stuff that's unimportant to us, right? As a structural engineer, I'm not concerned about the contents. I want to know things about the roof truss and the columns and the roof itself, right? And so
Yeah.
I'm able to with the point cloud, strip away the information that's not important about the structural system. See, we're able to clean out all that information and just reveal the structural system itself, which is really really important and interesting to us. So just to kind of highlight that, here's the marine storage building, and you can see there's the boat racks and all this stuff. And then here's the marine storage building where we've cleaned out everything and revealed the structural system. So there's some X braces here that you can't even see in this one, right? But in our virtual model, we're able to remove the boat rack that's here and actually reveal the structure that's behind it, because we took a lot of laser scans in this building, and the information's there. We just need to peel out, clean out the stuff that's not the structural system.
So did you manually clean it out, or did the computer do it itself, depending on the information?
Yeah, so we've got it's a little bit of both.
Okay.
There are some cool algorithms that we've written and other people have written that allow us to identify structural components and extract them from the cloud, but they're not perfect, and we often have to go in and do some of that manually ourselves. So here's another example, right, where it's this roof has collapsed, and what's really interesting is this roof system itself. That's how we're going to learn about what caused the building to collapse, what was deficient in the design of the building, and why it couldn't resist the hurricane level wind speeds. So we're able to identify the main structural components and extract them from everything else, so that we can make measurements and really learn about what the structural system was and how it failed. So really, really cool, interesting things. And then we saw in the beginning, we do these structural models. Well, we're able to go from, these point clouds, these 3D models, 3D point clouds, which are just, the geometry of the building, to actual structural models that help us understand the physics of what happened, right? And then from there, we're able to figure out why these buildings failed. And it turns out that a lot of these buildings failed. It was one structural element, or one kind of structural element, that was responsible for the collapse of most of these large volume buildings. And there are these little beams that hold up the roof, and they're called purlins. And these little beams, when the wind was blowing on these short walls, oh, sorry, that text is all messed up, but this is the windward wall. When the wind was blowing toward the short direction of these buildings, the roof is responsible for carrying that loading, that push of the wind against this short wall back to the X braces that are a couple bays back. And so these roof purlins are under an extraordinary amount of compression. They're being squashed in order to carry that wind pressure from this short wall back to the X braces that are back here, that are going to carry that load down to the ground. And these roof purlins, they're being squished, but also as the wind is blowing on this side of the building, it's also creating turbulence as it goes over the building, and it's also pulling those purlins up, and it's creating this big suction. So these roof purlins are being squeezed, and they're being pulled up, and they buckle. And as they buckle, the wall collapses, and it was the same failure mode in every single one of these large volume buildings that we went to investigate. And so from all of this 3D models and understanding the physics, and using our cool new technologies, we're able to understand why these buildings failed, and we're able to make recommendations about how to avoid this in future designs.
It's great.
And so that's kind of it. That was my talk, and I
All
think the big
right.
takeaways are, if there's four things to take away, it's civil engineers. We're working on really important, some of the most pressing problems that are facing society, and we're trying to, and as structural engineers, it's really challenging because we can't prototype. It's uncontrolled environment, and there's really high consequences for failure. But we're trying in civil engineering to use all these new technologies to help us better understand how our designs are performing in the face of at least natural hazards in the cases that I talked about.
It's great. Thank you so much. But we do have some more questions, so it's not over
That's
yet.
great. Yeah.
So this is towards the beginning. I think I
Mm-hmm.
asked how long does it take to build like a building, and you said
Mm-hmm.
10 years. This person asked, are there concerns with 10-year structure building process not being fast enough? For example, if you predict a natural disaster and you need it more immediately.
Oh, absolutely. Yeah. It's a speeding up the design and construction project process is actually a really, really big deal. And another way that we're using new technologies, in these cases, using technologies to help us automate some of the aspects of design so that it can get done faster, help us automate aspects of construction as well. All the technologies that I talked about can be used to help ensure buildings are constructed as they were designed. And we do use laser scanning and drones and things like that already to help us make sure that buildings are being constructed the way we want them to. And the 10-year process really, it's 10 years for some of those mega structures that I was talking about, right? But it's not a 10-year cycle for, a house, right? Or something, much smaller, right? So the scale and the timeline kind of go together.
All right. Sounds good. The next one is, what are some of the major constraints of designing a building besides not being able to test the entire building?
Yeah, I that's a great question. And the constraints associated with the building are, there's a couple of them. We think about, one of the big constraints is the site, the location where we're going to put the building. And that kind of defines a whole bunch of things. It defines in terms of loading, what we might think about for loading. It defines how fast, we know how fast we expect wind to blow kind of in every location in the US where we would design buildings. So the site helps us define things like the expected earthquake shaking, the expected wind velocities. It helps us define the soils that we're building the building on. And then the other constraints are really things that have to do with occupancy and use. So how is the building going to be used? And that's why, as a structural engineer, we work really, really closely with architects, because they're the ones that are, thinking about the functionality of a building and how it's designed, how kind of the building will look in the end, serves its function. And so that's probably the single biggest constraint involve kind of constraining the structural design, is making sure that the structure also satisfies the architectural goals as far as its use.
Okay. And I'm just curious because I haven't really heard you talk much about like what material the buildings are made out of.
Oh yeah.
Like, what is the optimal material, would you say?
Oh,
Like, I don't
yeah,
know.
that's going to be every every project, every different building is going to have its own optimal material, and it's going to depend on all those things. What is the occupancy and the use? What's the scale of the building? What are the loads that we need to think about when we're designing the building? Um, Certainly, like for small kind of low rise residential buildings, we do a lot with wood. And that's not to say that wood is necessarily the most efficient material for providing strength and stuff like that, but it's economically efficient for those buildings, and that's really important. We need to think about designing buildings economically. That's really important. When you get to skyscrapers and big stadiums and big bridges and things like that, we use a lot of steel and a lot of concrete.
So, like for example, about these like warehouses, were they all made of the same material? Is that why?
Yeah, those large volume buildings, and here's one of the images of one of those large volume buildings that had collapsed. Those were all steel buildings.
Oh,
They
okay.
all had steel frames, and then they had different things for the skin of the building, but the skin of the building is not part of the structural system. It's just keeping people dry on the inside, but
Oh, okay.
the structural system in all those cases was steel.
All right. Sounds good. Okay, the
Mhm.
next one is in a location that frequently faces two natural disasters of different types, what
Ooh,
trade-offs occur between optimizing the building to withstand both?
that's a great question. Um, so often, what we do is we need to design and think about both types of natural hazards. And often, what we do is we usually try to define the expected life of a building. So we might think of buildings today as being designed for an expected life of somewhere between 50 and 100 years.
Okay.
And and then we try to think about within the 50 to 100 years, what is the probability that it's going to see wind speeds of a certain velocity or earthquakes of a certain intensity? And we try to treat all of this, and it's complicated. There's a lot of math involved to do this, but we try to uh, consider designing for both hazards, but thinking about it probabilistically. So we use statistical methods to quantify the likelihood of those hazards occurring, and kind of whichever one is kind of a combination of most frequent and most intense is going to govern the design of the building. So we will actually go through a process where we think about kind of the intersection of how frequent that hazard is and how intense the hazard will be in order to determine which one is going to govern the design.
Oh,
But by doing that, we consider both, in that case, both hazards.
okay. All right, that's really interesting. Next one is, has Florida changed their building styles after these hurricanes, like Hurricane Michael?
Yeah, we're working on it. It's a slow process, and
Oh
there's a
yeah.
lot of
Mhm.
politics and things like that it's not as simple as just the engineering is actually the easy part, right? We know why these buildings failed, and we know how to do them better. But that's going to cost money, and it's going to require laws and rules, and an update of building codes and things like that. And that is a social process, a social and political process, and that actually is almost harder than actually understanding the why these things behave the way they did and
Yeah.
how to do it better.
Okay. That's really okay. The next one is there a way to design a road that is immune or is not affected to that landslide?
Oh yeah, absolutely, absolutely. And with a big enough budget, enough money, we can do that. So that landslide that I showed back at the beginning, that landslide is affecting. It's about maybe 2 football fields in width, maybe about 600 yards or so. And you could easily bridge the landslide. You could build a bridge that has foundations at each end, and is a bridge over the landslide, and the landslide will move underneath the bridge, and the bridge goes right over it with no problem, right? Kind of spans over the landslide. But that's going to cost a lot of money, and not be an easy design. So as with a lot of the challenges that we face in really in any engineering discipline, a lot of the there's a lot of trade-offs between kind of the right design as far as performance goes, but the most economical design as well.
Oh, all right. Yeah, I didn't really think about bridging. That's an interesting idea. The next one is, what happens to all of the destroyed material? Do they go straight to the landfill, or can they still be reused?
That is also a great question. Yeah, when natural hazards like this occur, it is a huge environmental impact as well. The debris and kind of the waste is enormous. And there's a lot of research going on right now to figure out ways to best recycle and reuse materials after big natural hazards like this. Unfortunately, today, most of this ends up not most, yeah, probably most of it's going to end up in a landfill. But we're trying to figure out ways of segregating, of separating out materials that could be reused after the disaster, and that has to be coupled with the idea that we have to recover in a certain time period, right? So the faster we can recover, the faster we can get people kind of back to work and back to living a normal life. That's important too. So it's this balance between the speed of recovery and the ability to go through these damaged buildings and separate out what is reusable and what is not reusable. And we're working actually on ways of using some of the technologies I've talked about, whether it's imagery, laser scanning, and also some what we call multispectral images, where you're not just getting red, green, blue, but you're getting other wavelengths captured in the images, to rapidly identify materials, so that we can rapidly identify what materials may be able to be reused, recycled, and what materials can't be. And so, again, using all these modern technologies, I think we can do a better job than we're doing today in helping to lessen the environmental impacts of a lot of these natural hazards.
That's great. Okay, and the next one is, what less do we learn from Fukushima nuclear site? I don't know much about this, but
yeah. So Fukushima is the nuclear power plant that was damaged in the Tohoku earthquake and tsunami in 2011 in Japan. And that they had a nuclear reactor fail, and there was nuclear fallout. And in regions near the nuclear power plant are probably uninhabitable for a very, very long time, and it's a very expensive cleanup effort. It's one of the worst nuclear disasters that have happened. That has happened, and we're actually learning a lot about nuclear facilities in earthquake and tsunami regions, regions that are where there are significant natural hazards. We're learning a lot about the cascading way that failure happens in some of these really complicated infrastructures, like a nuclear power plant, and ways that redundancy can be built into these systems to make them pretty much fail safe. And in this case, in Fukushima's case, what the major failure occurred because the backup generators that were used to cool the fuel rods, the nuclear fuel rods. So nuclear power plants are really complicated, but we have to keep the fuel rods cool. That's one of the major issues. And if you don't keep them cool, they break down, and that's what causes failure in a nuclear power plant. And the way we keep them cool is by cycling water through, cool water through. But that water needs to be cooled itself. And what happened in Fukushima is that the earthquake knocked out some of the generators that helped to keep the water cool, that in turn cool the fuel rods. They had some backup generators, but the backup generators were not at an elevation tall enough to not be impacted by the tsunami. And they ended up underwater in the tsunami, and the backup generators then were not functional. And so then the fuel rods couldn't be cooled, and it failed. So we're learning a lot about thinking hazards all the way through in these really complex sites, thinking about cascading failures, thinking about redundant systems, and how each of those components needs to be robust and efficiently designed and thought about. And because we're learning a lot from that, we're actually, I think, able to do it a lot better today than we were doing it then.
It's great. Right. Well, I think those are all the questions.
That's great.
So, thank you so much for your time today. I really did learn a lot. I asked a lot of questions. So thank you for being a great and patient speaker today. So if you have nothing else to say, I guess that's it for today.
Yeah. No, I hope my big hope was, to get some kind of future leaders to be thinking about civil engineering as a pathway for all of the we need people who understand math and science really, really, really well to be coming into civil engineering and help us think about solving these really pressing world problems. So thanks for the opportunity to talk to such bright folks.
All right. Thank you so much. Thank you, everyone else, for watching and coming today, too, and for all these great questions. All right. Bye. Thank you.
Bye.